Welcome to the first in a series of webinars adapted from the recent publication, Advances to Dryland Farming in the Inland Pacific Northwest. My name is Liz Allen and I'm a research associate at Washington State University's Center for Sustaining Agriculture and Natural Resources. This webinar series has been sponsored by the Regional Approaches to Climate Change Research Initiative. And in this video, I'll explore some of the reasons why it's increasingly important for dryland small grains producers to consider climate science. Growers in our region are adept at managing for many different kinds of risks, and managing under observed and projected climate change impacts will require producers to develop their understanding of climate-related uncertainties and hazards. So today we will explore how climate influences dryland agriculture in the inland Northwest. We'll look at projected impacts of climate change, and I'll provide some examples of how producers can learn from and apply information from models to a broad range of production management decisions. The region that we focus on in the REACH project and in the Advances Handbook is located within the Northwest United States, indicated by the gray area that you see here on this map. This zone is sometimes identified as the Columbia Plateau ecoregion. There's considerable variability in terms of topography, rainfall, and soils within the inland Northwest dryland wheat-growing region. Climate has always had a dominant influence on rain-fed agricultural production decisions, influencing crops, management choices, and approaches to conservation. So the Cascade Mountain Range, which is indicated here with a white arrow, creates a rain shadow effect that results in the precipitation gradient we see in the Northwest. Moist air currents coming inland from the Pacific Ocean cool as they move up the western face of the Cascade Mountains, which causes precipitation to fall as rain or snow because cool air holds less moisture than warm air does. So this results in us seeing immediately east of the Cascades conditions that are significantly more dry and then becoming slightly wetter again as we move further inland. Agricultural systems in the inland Northwest have been developed and refined over time to be well suited to the climate, which is generally characterized by warm, dry summers and cool, wet winters. Precipitation is the primary limiting factor of production for most of the dryland wheat-growing region. For example, as you can see in this climograph from Moscow, Idaho, most of the precipitation indicated by blue bars falls during the winter and early spring months. Summers in the region are markedly warmer and drier. Looking at this climograph, we can actually see that historical average monthly precipitation ranges from about 3.5 inches in the month of November to just under an inch in August, and average monthly mean temperature, which is indicated by the black line, ranges from about 29 degrees Fahrenheit in December to 66 degrees Fahrenheit in the months of July and August. Soils are also highly variable within the inland Pacific Northwest. The region's soils were formed by wind-blown silt deposits over basalt bedrock or flood-deposited sediments. In the drier, warmer western region of the inland Pacific Northwest, the soils developed under steppe and shrub steppe vegetation, and they're generally low in organic matter, more sandy, and susceptible to wind erosion. In the cooler, higher precipitation zone of the inland Pacific Northwest, which includes the Palouse Hills, the soils developed under native grasslands and forests and are richer in organic matter and clay. These soils are susceptible to water erosion when snowmelt or rain runs over recently thawed topsoil. Throughout the region, production practices are suited to unique local conditions. Local climate patterns are highly variable from one location to another because of the area's geologic history, which has led to distinctive landscapes and soil types. For example, here's dryland wheat producer Ron Giray of AK Farms in Adams County, Washington, describing the local conditions where he farms.
Where we're located here is mostly a rolling topography. There's nothing real steep for any length of distance, but there is a few steeper spots that give us a little bit of problem. The soils are all a Ritzville silt loam, real kind of fragile at times, and we're doing 6,000 acres now. Let's see, and we're farming mostly wheat with some spring wheat that's annual crop no-till, and then we've got some chem fallow or no-till fallow that we're putting both winter wheat and winter pea on that we're working with. So
The arid region where Mr. Duray farms represents one specific class of agricultural land in the inland Pacific Northwest. The diversity of farming practices that are driven by differences in soils, topography, and local climate conditions can be observed in this map of agroecological classes defined by REACH scientists. Climate influences cropping systems that producers choose. For example, in the Palouse near Pullman and Moscow, indicated by a red star on the map here, producers rely on sufficient soil moisture and do not need to fallow their fields, typically. This land is classified as part of the annual crop agroecological class. Moving to the northwest near Davenport, where you see a pink star on the map, crop choice is limited by available water, and farmland is in the annual crop fallow transition class, where a typical 2 to 3 year crop rotation will include a period of fallow. Here we're looking at the agroecological classes for dryland farming systems in a bit more detail. Land in the annual crop class is farmed with a 3 to 4 year crop sequence. For example, winter wheat followed by spring grain, then winter wheat and a spring broadleaf. In the annual crop fallow transition class, farmers use a 2 to 3 year crop sequence. For example, here we're looking at winter wheat, spring wheat, and then a period of fallow. In grain-fed systems, the rotation is generally winter wheat, then fallow. The agroecological classes are defined using actual cropland use data as it's reported by producers. So this system is based on percent fallow rather than the underlying climatic factors that shape the decisions producers make. And focusing on actual land use allows us to analyze the relationships between climate, soils, terrain, as well as social and economic variables, such as land prices and the actual commodities that are grown. So this agroecological class framework makes it possible to predict changes in classes caused by projected shifts in climates, markets, and management practices. For example, REACH researchers have projected that we'll see increased water use efficiency and wheat productivity occurring through most of the century in the inland Pacific Northwest. So in this future scenario for the year 2070, the fraction of regional area occupied by continuous annual cropping, which is the most intense cropping system, is projected to increase, while grain fallow, the lowest intensity cropping system, would be projected to decrease. The area in the annual crop fallow transition class under this projection remains basically the same. And you can read about these results in the 2016 REACH Impact book, which is also available online, and it will refer you to some forthcoming publications exploring these findings and considering the potential impacts of climate change and agricultural innovations in the region. Historically, the climate in the inland Pacific Northwest has been sufficiently stable to support dryland small grain production that rivals the productivity of nearly every other rain-fed cereal producing region in the world. Production practices that enhance the sustainability and dependability of dryland cropping systems in the inland Northwest are critically important in the context of global climate change. Now I'd like to say a little bit about how climate and weather influence farming decisions more specifically. We tend to talk about weather on a 1 to 10 day scale, while climate plays out on the seasonal scale. It's widely understood that weather shapes production management decisions, including choices about when to harvest, plant, and fertilize crops, because weather conditions affect freezes, frosts, and heat stress. Now, climate plays out over the longer term, also affects producers' decisions. For example, long-term planning issues related to land management, variety development, and selecting cropping systems. Researchers collect long-term data about weather. We can assess climate in the region in part by looking at the history of this data. Here's Dr. John Abotsoglu, Associate Professor of Geography at the University of Idaho, on location at the Parker Farm Weather Station outside of Moscow, describing the network of weather data stations in the Pacific Northwest.
We collect a number of observations from stations like these across the world, and here in the western United States, and specifically across the Palouse. Namely, we're collecting daily observations of temperature, both the high and low temperature for the last 24 hours. We're collecting information about accumulated precipitation. We also are able to estimate the rate of pan evaporation, or basically the water loss. And then when it snows, we do measure snowfall accumulation and snow depth. There are other observations that are collected from this particular site, including wind speed, and then a lot of also atmospheric gases and particulates. So there's a lot of weather stations in the region. There's everything from stations at airports that were put out specifically for air traffic control. We have stations from people who are citizen scientists. I have 2 stations in my backyard, in fact. And then we have a number of official stations that are basically sanctioned by the National Oceanic and Atmospheric Administration. And this is one of them behind us. This is one of the stations of around 1,200 in the United States that is a long-term station, is located in an area that hasn't seen a lot of change. It's not located in an area that is, highly urbanized, and it has a fairly complete record. And so this station, as well as several other, in fact, there's a station in Pullman that is also one of the long-term records. We have on the order of 40 or so stations in Idaho, 40 or so stations in Washington, 40 or so stations in Oregon that are all sort of these official long-term observation networks that are so-called climate quality. When developing models of the atmosphere and models of climate, we don't use this data that's collected here per se, but what we can do is we can take some of those models that are relying on other principles, and then we can further refine them. So the models that we produce, they're usually at really, really coarse global scales. It's like 1 pixel would basically span between, Lewiston and Pullman and beyond. And so we can provide some additional granularity or spatial resolution by basically taking information from stations like these and basically correct for the differences between what the model produces and what these stations produce. And that provides us with some additional realism. And that's obviously important. We'd like to use the most realistic, scientifically credible simulations of climate to say what's going to happen in terms of the future, sustainability of agriculture. It's important to collect long-term observations of the environment. Climate is one piece of it, but we'd like to know what has happened through time. We want to be able to track, just how much variability we have. So from this station here, we actually can get a lot of information about climate, and climate is in some cases what we expect, weather's what we get. There's that old adage. But climate also, in information collected from this station here, we also get an idea of, how much has ever actually fallen in terms of precipitation in one day? How much snowfall have we seen in one day? How cold has it ever been? And the numbers are actually fairly impressive. This station here got down to negative 42 degrees Fahrenheit in the late winter or late December of 1968, and it's been up to 109 degrees Fahrenheit. And so that range of variability is critically important, and tracking all the ups and downs over, this station has been out for over 120 years. Not in this particular location. It's actually relocated a few times, and we have to find ways to deal with that. But observations about our environment are critical, whether it's this station here or weather station. Up on Moscow Mountain, that's just a bit behind us here, we have a Notill station which collects information about snowpack. And so collectively, using all the environmental information we have a pretty good idea of what our region is capable of, what sort of variability we have, and what sort of changes we've seen. How long of a time period do we need to get a good idea of what the climate is like in an area? And so typically we think about 30 years. So the idea is we're taking observations every day for 30 years from this station. It's a pretty laborious job. The guy who's actually been doing this job for the last, I want to say 37 years, he comes out at 5 p.m. every day, rain, shine, snow, whatever, like the mailman. And he tracks observations, and he actually keeps it in a log, and we'll see that log in there. And we need about 30 years to get a good idea of what we expect, what the ranges are. When it comes to looking at changes in climate, you can do something with 30 years, but it's sometimes a little bit challenging. And that's why it's really important to have these long-term stations out there. And so this station, 120 years of data. With that, we can say something about changes through time.
So here we have a map showing some of the stations that are part of the official network of weather stations collecting temperature and precipitation data in the Northwest. These weather stations help us understand the spatial variation in weather and climate conditions. It's really important to note that data from one location may not perfectly reflect conditions even just down the road. For example, there could be micro-scale processes like cold air drainages. That said, we use satellite data to assess and make projections about the climate conditions between stations. In addition to all of the spatial variability that we see in the region, year-to-year variation in temperature and precipitation is considerable and is normal in terms of the historic record. Here we're looking at historic climate from the Climate Tracker tool at one point near Moscow, Idaho from 1979 through present. These charts show maximum temperatures on the left side and total precipitation on the right-hand chart during the month of May for each year. You can quickly get a sense of the considerable variability in weather from one year to the next and of the cyclical nature of warm and cool years and relatively wet and dry years. These year-to-year variations in local conditions are caused in part by cyclical climate processes that influence the whole region. There are several climate processes occurring simultaneously with cycles of 3 to 10 years, for example, the El Niño Southern Oscillation, or ENSO. In the ENSO cycle, there are fluctuations in Pacific Ocean sea surface temperature that originate near the equator and then have impacts that lead all the way up into the Pacific Northwest. During El Niño years, tropical sea surface temperatures are warmer than normal, leading to warmer and drier conditions in the Northwest. In this map of the Pacific Ocean, we're looking at typical El Niño conditions. The yellow and red colors indicate warm ocean water temperatures. You can see how warmer ocean temperatures start with the yellow zone in the center of the map in the middle of the Pacific Ocean, and this leads to warmer water all along off the west coast of North America, which has a big impact on climate as far inland as Moscow, Idaho, marked with a red star on this map. La Niña years are the opposite, with cooler than normal sea surface temperatures, which result in wetter and cooler conditions in the northwest U.S. So here we can get a sense of the cyclical nature of annual mean temperatures from 1900 to present across all of the Pacific Northwest by focusing in on the black trend line shown on this map. The red bars indicate warmer than average years, and the blue bars show cooler than average years. We're all familiar with weather forecasts that we might see on a weather app on our phone or on the nightly news. These forecasts come to us from meteorologists at the National Oceanic and Atmospheric Administration's National Weather Service, as well as other international research organizations. From our experience with forecasts, we know that there's great skill in projecting what the weather will look like in 1 to 3 days, but considerably less accuracy when we start talking about projections of more than 3 days in the future. It's important to know, though, that just as there are teams of NOAA meteorologists tracking atmospheric processes to provide those near-term forecasts, others, including at the NOAA Climate Prediction Center, are developing seasonal forecasts. These longer-term climate projections rely on models of slower evolving components of the weather systems, including the climate cycles we just looked at, as well as soil moisture and snow cover. Some climate modelers look even further into the future, focusing on long-term climate projections rather than daily or monthly forecasts. Global climate models simulate oceanic, atmospheric, and land surface behavior, but with really big grid cells. So for example, 6 grid cells would cover the entire state of Idaho. There's multiple different global climate models which differ in how they account for all of these Earth system processes and how they fit together. So while there's variation in the projections among different global climate models, they are all consistent in projecting an increase in global average temperature in the future due to rising greenhouse gas concentrations. The REACH research project made projections at a more detailed spatial resolution by using station data to consider the effects of local topography and look at regional climate futures projected by 20 different global climate models. Different global climate models make different assumptions about how atmospheric, oceanic, and land surface processes will interact, and that is one source of uncertainty and variability among different climate models. But there's also uncertainty caused by the fact that we don't really know how humanity will make decisions about energy and land use, which will then affect the concentration of greenhouse gases in the atmosphere. Greenhouse gases in Earth's atmosphere cause more of the sun's incoming radiation to be trapped as heat. And so because of uncertainty about future emissions and future land use management decisions, climate modelers really need to consider a range of different scenarios for greenhouse gas concentrations. Here you can see projected summer maximum temperatures through the end of the 21st century for Moscow, Idaho, under two different greenhouse gas emission pathways or scenarios. The red line represents future summer maximum temperatures under a high emissions scenario, whereas the blue line represents summer maximum temperatures projected under a lower emissions scenario. Now we're looking at temperature projections for southeast Washington state under those same two different greenhouse gas emission scenarios. You'll see bars for historical annual mean temperature in the 2040s through 2060s, with low greenhouse gas emissions in the center bar and high greenhouse gas emissions in the far right bar. Even under a scenario of low emissions that peak in the year 2040 and then begin to actually decline, we'd still project substantial temperature shifts in the Northwest. This spread of projections that you see here on this chart reflects all of the different global climate models that were considered. In the inland Pacific Northwest, average temperature increases of 3 to 4 degrees Fahrenheit are expected by 2050, and annual average warming of 4 to 6.5 degrees Fahrenheit is expected by the year 2100. Warming trends are projected to be greatest in the summer months. Climate models also project greater temperature extremes, both in terms of minimum and maximum temperatures in the future. When rising greenhouse gas concentrations cause warmer air, that air holds more water, and so we can expect precipitation to also increase under climate change generally. But it's usually much more difficult to actually make projections about how precipitation patterns will shift under climate change because there's so many local topography effects and such. Annual precipitation is projected to increase 5 to 15% by the latter half of the 21st century. Here we're seeing a projected increase of about half an inch from the historic annual precipitation average under a low emission scenario for 2040 through 2060, and an increase of roughly an inch in the high emission scenario. Importantly, while total annual precipitation is projected to increase under all of these global climate models, summer season precipitation would be expected to decrease. This, combined with elevated summer temperatures, could result in a reduction in late summer soil moisture. In terms of what these projections mean for planting dates, crop maturity rates, and pest and disease management, there will be significant impacts by the end of the 21st century. Now we're looking at projected change in growing degree days under a scenario of high greenhouse gas emissions for the decades from 2040 through 2069. Growing degree days are used to estimate the growth and development of plants. The basic concept is that development and growth will only occur if the average daily temperature exceeds some minimum development threshold. Here that's 32 degrees Fahrenheit. Growing degree days are used in crop models to project plant development rates and to help us determine when crops would be expected to reach maturity. So the map on the left shows average growing degree days based on historical data, and the right is the future projection for those decades between 2040 through 2069. And you can see substantial change in the growing degree days throughout the Northwest. In some areas, we may see crops reaching maturity earlier in the growing season, and crops may experience heat stress, which accelerates the rate at which wheat dries out. So these projected shifts could increase the challenges for growing on marginal land, potentially. To recap the projected climate change impacts in the inland Pacific Northwest, warmer, drier conditions are expected to exacerbate wind-caused soil erosion and to reduce early stand establishment of winter wheat on summer fallow. At the same time, there may also be more extreme storm events and heavy precipitation events due to the fact that warm air is more energetic and holds more moisture than cool air. These changes have the potential to affect the viability and effectiveness of the cropping systems that have historically been implemented throughout the inland Pacific Northwest. But not all expected impacts of climate change in the region are exclusively negative for producers. Some recent crop models suggest crops will grow faster due to higher levels of carbon dioxide in the atmosphere, and we call this effect the carbon dioxide fertilization effect. And the REACH project used climate and crop models to understand how carbon dioxide fertilization, combined with innovations in farming technology, may potentially offset most or all of the negative impacts of projected future climate change on small grains crops. REACH researchers looked at opportunities to successfully manage dryland farming under a changing climate with approaches including improving soil organic matter by switching to reduced tillage and no tillage, diversifying cropping systems, including changing planting dates, managing for and monitoring changing weed, disease, and pest pressures, as well as selecting for new varieties and new crops that may better tolerate an altered climate. REACH research seeks to provide resources for producers exploring these new approaches and new crops. For example, this could include incorporating canola in rotations. Producers in the Northwest also have opportunities to mitigate or lessen the severity of projected climate change by reducing their greenhouse gas emissions and enhancing carbon storage in agricultural soils. Mitigation strategies focused on supporting healthy soils address other long-standing challenges in the region tied to erosion, organic matter depletion, and soil fertility loss. Here's Ron Geray again from outside Ritzville, Washington, describing the considerations that led him to implement a no-till system.
We've been doing the continuous spring wheat under no-till since, if I remember right, 1996. In the process of doing that, we've tried other crops on small acres and had lots of issues along the way, and found that it was just as easy for us to deal with it by just continuing to use spring wheat on the project. So that's what we've been doing on the spring wheat no-till. And then about 6 years ago, maybe 7 now, we started doing some no-till fallow for winter wheat. And that was working, it's working so-so. We're still learning the ins and outs and the weed control and a few of the other things with that, how to handle the fertility. And then this year we also decided that we're going to put winter pea on with that rotation. So we've actually got winter pea on some of our no-till winter fallow or no-till summer fallow, as well as winter pea in the conventional or quasi-conventional stuff that we do with the hay buster. When I first switched, it was because I didn't have a lot of acres, and if I wanted to put spring wheat in and crop more acres in a year, doing it conventionally, having to make 4 or 5 trips over it in the spring to get the ground ready, just didn't make any economic sense. And being able to just go out there and spray it and be able to do it all in one pass just made a whole lot more sense. So that's kind of how we got started on it. The summer fallow, no-till, we got started with that on, believe it or not, a drought year. It was just so dry that we're going, if there's nothing in the fall to seed, moisture in the fall to seed into, why are we going to beat this ground up too much and have it blowing and everything else? And so we just we left a half section of ground set and started playing. And that's how we kind of got our foot in the door with the no-till summer fallow. And so we've been trying to have that, a little bit of that every year in the rotation since then. What we've found this last fall when we were seeding peas is it's so much easier to seed into than having a bunch of mulch on top that's got a lot of straw that you got to pack or blind seed beforehand to get through it. So it's just if the straw is anchored there, you just go right through it, no problems. And the other thing that we found that is real nice and exciting for that matter is the fact that if it rains on the stuff that we use on the summer fallow, no-till summer fallow after it's seeded, if it rains on it, it doesn't crust. We don't have to worry about it crusting. It'll all come up. Where on the conventional fallow, if we get a rain on it, the soil particles are small enough and things are loose enough, it'll pack it and it'll change the bulk density of that soil enough that it'll curl the wheat as it tries to come up if it's not up, and then you're out there reseeding and with that expense. So that's one of the nice surprises behind that we've found so far, that don't have to worry about rain on it in the fall after seeding. So, well, I think the social aspect of what we need to pay attention to as we continue to manage our farms is just that fact that there are fewer and fewer of us and more folks in the city. And so they have their opinions about how they want their food produced and where they want it to come from and all the things that go along with that. And we just have to keep that in the back of our mind, that we are producing for a customer. But we as producers are also concerned with our own environment, because we want this stuff to be around, we want the soil to be around for the next generation and the next generation, the next generation. We're the ones that are out there using the pesticides, the herbicides, and the insecticides. We sure don't want to be getting sick or making our children sick or anything else.
But as Mr. Duray points out, in order for it to be practical for producers to implement conservation practices, location-specific approaches have to be refined, and regulatory and financial systems must evolve to support producers in making these shifts.
The no-till, especially on the spring wheat, the annual cropping side of it, is it's effective in a lot of ways. In this area, though, it's not the most economical because we're limited by moisture. We're 11 inches, approximately 11 inches annual precip average, and the averages of two extremes, and so we fall below that average on moisture, and it can be pretty devastating to the crop yield, and consequently devastating to the income. And so it's it's highly variable, where the summer fallow, both on the no-till side and the conventional side, is a lot more stable. The public needs to be aware of the costs that are involved, because the payback for the producer may be zero or very long term, depending on what the practice is or what they do. But for the public, it's almost immediate, because it's that water's not coming off anymore. You're not having water wash a ditch or something, or the dust isn't in the air. Machinery nowadays is extremely expensive. So making a change to a complete farming operation in practice, in the way they do their farming practices, can be economically preventative.
Making changes to production practices isn't easy, but producers are adept at managing under multiple different kinds of risks and uncertainty. However, because climate change happens very slowly over time, and because there's multiple sources of uncertainty and a lot of local variability in projections, it can be especially difficult for producers to incorporate climate change science into their decisions about investments and about management practices. But we do increasingly recognize that state and federal regulatory agencies are looking at climate data when they make new regulations and establish new policies. And insurance companies and lenders are also looking at climate data to make decisions about rates and about programs and policy. So there's many reasons why it can be an advantage for producers to understand more about future projections of climate change on the land that they farm to ensure the long-term sustainability and viability of their cropping systems. Agricultural decision makers need information about the historical climate as well as projections for the future, both those near-term seasonal projections and long-term, long into the future projections. Here's Dr. Catherine Hegovich, postdoctoral researcher in the Department of Geography at the University of Idaho, describing some of the tools that are available for producers to understand climate science.
So these tools provide access to both historical climate data and then also seasonal forecasts for the next 7 months, and then finally future climate projections over until the end of the 21st century. So those are the 3 climate data that these tools provide visualizations for. So we have 2 tools for seasonal forecasts for the next 7 months. One of them is the Seasonal Forecast Maps tool, which shows maps of forecasts of temperature and precipitation for the next 7 months. And we have another tool that for your location, such as in Moscow, you could see what the seasonal forecasts are for just your location to make that more real. And we have a tool called the Future Time Series tool that shows a time series of future projections of temperature and climate over the 21st century using 20 of the global climate models and both a high and low future greenhouse gas emission scenario. So some of these tools show pure climate variables like temperature, precipitation, humidity, and wind speed, while other tools show more agriculturally derived variables like cumulative growing degree days or coldest winter day, hottest summer day, dates of the last spring freeze, the first fall freeze, or cold hardiness zones. So producers can use our climate tools to inform their knowledge about the past climate of their location. They can get a glimpse into the coming spring as to if it's forecasted to be wet or dry or warmer or cooler than normal and make decisions based on that. And finally, to use the future projections to understand how their current cropping system might fare and if they need to make adjustments to their operations in the future.
We encourage you to refer to the Climate Considerations chapter in the Advances to Dryland Farming Handbook for a full list of relevant educational resources and tools about climate science that are available to producers. You can also visit the Northwest Climate Toolbox and access these decision support tools that focus on near-term projections, seasonal forecasts, and long-term future climate projections. Climate change impacts in the Pacific Northwest will require producers to consider adaptation and mitigation measures that are well suited to the unique local conditions where they farm. This latest edition of the Dryland Farming book highlights the work being done to understand what appropriate management solutions may look like in different places and different cropping systems. At the same time, we as researchers are continually refining tools available to producers to better understand and plan for the risks and opportunities related to the changing climate of our region. Thank you for watching, and please share any questions that you have with us.
So the first one we're going to do is from Patrick Binns, and he's asking, could you describe how the projected increase in growing degree days impact the timing of the planting season for key crops in the IPN or the Inland Pacific Northwest region?
Yeah, good. Thanks for that. This is Liz here, and thank you again, everyone, for being here watching this morning. I want to sort of right off the bat here tell you all that I'm not an agronomist. The research that I do, I'm really interested in kind of the bigger picture questions of how land use decision makers can use and access and learn from climate models. So there's going to be some more in-depth information available on the REACH website that can kind of get into the modeling that's been done to look at how the projected climate change or projected change in growing degree days could impact specific crops. So I guess kind of the first thing to note is that the growing degree days are a measure of heat accumulation, and those projections depend a lot on your specific location and the crop, since different crops have different base thresholds for the growing degree days. So different temperatures that they're set on to measure the difference in daily average temperature versus that base threshold. And Catherine might want to jump in and say a little bit more here too, because the Northwest Climate Toolbox is developing more tools to help producers look at these questions.
Right.
I don't know,
And
Catherine, if you want to jump in.
yeah, so we do have data to answer the question as to how these projections are the projections of the growing degree days. For impacting the planting season, we do expect that the growing degree days, there's going to be more growing degree days, and also for every year, but also that the first spring freeze, the last spring freeze and the first fall freeze are going to change, and that's probably going to be the biggest impact on planting, impacting the timing of when the planting starts. So for example, for the winter wheat, which is a primary crop in our inland Pacific Northwest, they'll have the flexibility to plant later than the usual October 1st, as the first frost from the winter will be coming later. So there's going to be some flexibility in there. And for the spring wheat, they'll have the flexibility to plant earlier in the year. And since our growing seasons are going to be longer, there can be flexibility as to when to plant, even if you want to go later in the season, because the wheat will have more time to mature. So the answer could be that there's going to be more flexibility for producers as to when they plant and designing the crop growing season.
There are a few more from him, and then we also have some from Carl and Rosalie DePaul. So the first one we're going to tackle is regarding climate variation. Any considerations given to landscape aspect in the modeling effort?
So with this question, I think, maybe you're asking about this, how we model climate change impacts on this regional or more local fine scale. And so as we downscale these global climate models to look at projected impacts on the sort of regional scale to the field scale, the aspect or the positioning of landscape features definitely does factor into how those downscaled models are developed and created. Again, Catherine, maybe you have more to add.
Yeah, so there is a land surface model for the global climate models, and they don't allow them to change, but yeah, so they don't really allow the landscape so much to change in the future climate models. But there is consideration on the landscape part. There is a land surface model, and there is vegetation models for different parts of it, but it's pretty much what is there now. Yeah, and so that's all I would have to say, actually.
Okay, so we have another question from Patrick. So how are extreme heat or cold weather spikes monitored? The timing and duration of such abnormal events can significantly impact crop growth, especially with regards to the stage of growth of specific crops that are exposed to such short-term weather volatility.
And I'll take that one just quickly. So the weather stations do record temperature at the hourly scale, and some weather stations might record even at a finer scale than that. I'm not actually sure if I've only seen hourly temperatures. So there is data to capture some of that timing and duration of those abnormal events like the heat and cold weather spikes. However, normally due to the size of such hourly data, like for some of the tools that we make, we only utilize summaries of the daily data. For example, looking at the maximum and minimum daily temperature. And so that's what you'll see in our tools. But you're right that that just the maximum and minimum daily temperature isn't summarizing the timing and duration of temperature spikes. And so that's something that maybe could be done better, to take summaries of hourly data that is coming from these weather stations, which might better capture these temperature spikes.
All right. And let's see, here was another question. So one of the projections, this is from Villicus Farms. One of the projections I've seen from climate models are for increased variability in the amount of intensity and timing of precipitation. I am concerned that this increased variability and occurrence of both heavy and extremely light precipitation events will be much more impactful than the change in averages. Please discuss this.
Yeah, this is absolutely a good point to raise. And just to kind of recap what we see with climate change and changing in the warmer average temperatures just means increased energy in the whole hydrologic cycle. And so we see larger and more intense storm events. and also just this change towards greater extremes in terms of drought conditions and also potential heavy precipitation events. And modeling capabilities, I mean, this is like one of the most difficult things to model, but our capabilities are developing and evolving to be able to better anticipate some of those, and also I think to sort of project on the decadal scale what sort of to bound what we may see. But yeah, this is absolutely a good point that for producers, it's a huge concern.
All right. And let's see, another question from Patrick Binns. Could you discuss the expected changes in the need for irrigation to compensate for less precipitation over the summer months?
Yeah, so for the study region that REACH looks at, these are sort of cropland that currently is not irrigated, and you know, I don't think that we anticipate seeing opportunities to incorporate irrigation into these cropping systems in this specific region. Yeah, some of these questions I would love to kind of even take them back to some of the other research team and see if we can get a written response up online to address this, because I think in other parts of the region, it's definitely a consideration of trying to understand.
And we're going to have, and we're in this webinar series, we're actually going to be dealing with a lot of different things, not just this. And so one of the other presenters might have more information on some of the questions.
Yes.
And also, this is part of Advances in Dryland Farming in the Inland Pacific Northwest, which is a book by REACH, which I will actually give a link to at the end of this webinar. All right. So can you say more about the 7-month forecast models and how to access and use them? There will be a lot of interest in such a tool for making decisions for flex farming operations.
Yeah, so I'll take that question. So everybody you can see my screen, I think. So I'm sharing my screen, and this is a screen of the Northwest Climate Toolbox. And the seasonal forecasts are produced by the Climate Prediction Center at NOAA, and they are based on more slowly evolving parts of the climate system, like the phase of ENSO that you're in, and the persistence of snow cover and what this current soil moisture is. And they use those pieces of those in their climate models to kind of predict in the next 7 months just generally what's going to happen about increases in temperature or decreases in temperature, and about temperature and precipitation. And so what we've done is we've made these projections. We've removed some biases from some of these forecasts, and you can access these forecasts at the Northwest Climate Toolbox, which you can get by going to climatetoolbox.org. And specifically so when you arrive at this page, there's a list of tools, and there's 2 tools that are relevant. There's a seasonal forecast maps, which you can click launch tool to get. And then there's also the seasonal forecast plots, which is where you can pick your location and you can actually see what the projections are for your location. So I'm looking at this tool now. And so for example, you can select your location, and I can put in Moscow, Idaho, and you can get projections for the temperature of Moscow, Idaho for the next 7 months here. So here's mean temperature, and it's showing both the average in the black line and then also what the projections are in this blue line, and it gives you a range in the shading of the variability also between the different models. So this is how you can access those forecast projections. And then I can't remember if there was another question. Let me just see.
So they also had, I think you may have answered some of this, but they also had the question that what tools can farmers use to get more climate information if they don't have access to weather data? And you at least somewhat answered that.
Yeah, actually, I think there's another answer to that. And so if you don't have a weather station on your property, which a lot of some farm producers do, but so they're taking their own long-term they have their own access to long-term records on their property. But we do have access to gridded data here, observations for since 1979. And I would actually say that the climate normals tool and the climate tracker tool, these are two tools that'll give you information on your location. So again, you can pick your location, and and these are gridded over the whole contiguous USA. And so within a 2.5 mile grid, you should be able to find some data for your location. And you can get information on what the average precipitation and average temperatures are for the different months. And then also in the climate tracker, you can get some information on the variability in some different metrics, some precipitation and temperatures and wind speed for some different months of the year. And you can get information on the what's been happening in that 2.5 mile grid since 1979. So that's two ways that you can access some historical data.
We have a few more questions now. So here's a pretty specific one. Is the change between night and day temperature increasing, especially in the autumn? Will there be more dew during longer periods in the morning and in the future?
This is a really interesting question. I haven't seen any data on this, although it's very possible that John Abatsoglu, who you saw in a segment of this video, may have more information on that. And so this is another question where we can follow up and try to get an answer. And Catherine, maybe you actually might know about this too.
Yeah, so the variable that we'd be looking at here would be the diurnal temperature range. And we haven't produced summaries on the diurnal temperature range. It's the change between the night and day temperatures. It would also, for our tools, would be the difference between the max temperature for the day. And we have done some work in looking at those things, but I do not off the top of my head know what the projections would be.
Okay, and are there any possible tools is there anything that he could go to in order to see that?
Yeah, we don't actually have the diurnal temperature range as an option, but you could kind of tease a little bit of that out by looking at the max and the min temperature from some of these graphs between night and day temperatures. Yep, so by looking at the max temperature and the min temperature separately, we just don't have a tool to specifically look at that. But the data is in the tools, so you could try to figure some of it out. Yeah, and I think one way to do this would be like looking at, there is the future time series tool, which does have, so it's looking at maximum temperature for a location. So again, we could pick our location, and you can also pick a season. So you said in autumn that you might be interested in seeing if there's a difference. So we could look at max temperature and see what the projections are. And then you could see, like, for instance, that historically, maybe it's starting at 67 Fahrenheit, it's ending at 77, so about a 10-degree Fahrenheit change. And then for minimum temperature, you can do the same thing for autumn. So there is a way to do it. It's just not as clear. And here for minimum temperatures in the day, it's 41 to 51, so it's about 10 degrees also. So that's just the average from the global climate model. So there's a way to kind of use these tools to get at some other questions. I guess that's what I was trying to illustrate just by looking at this tool.
So Binglian Liu asks, why no tillage on spring wheat? Or why is no tillage on spring wheat not economically sensible? What is the large disadvantage of no tillage over conventional tillage practice?
Yeah, so I think you're responding to a comment that Ron Duray made in his interview on this video, where he talks about kind of the economic challenge of making the switch to an entirely no-till system that he used. And I think he's really referring to those short-term upfront costs of the tractors and the drill that are specific to having a no-till system. So it requires kind of an investment in all new machinery. And I think in some analyses, sort of the long-term costs, start to balance out, but it's that initial economic challenge. And again, this is something that I'm interested to hear some of the others on the REACH team weigh in with some more details about it. In terms of the large disadvantage, one thing that I do tend to hear is sometimes in no-tillage systems, more pesticides are required to control weeds. And again, that might be something that Stanford can address in the pests and disease webinar coming.
All right, let's see. Let's go with, oh, we are actually very close to running out of time. So I'm going to go with one last question, unless anybody wants to get in a few more before we leave. But I'm going to answer James Rowe, who asked, will a copy of the presentation be sent out to or made available for participants? Yes. It's not necessarily going to be sent out by email, but it will be available on climatewebinars.net, as well as on the REACH website, I believe. The REACH website one will just have the video and the question and answer session, whereas this will have the one on the climatewebinars.net will actually have the full webinar.
I mean, I guess I just want to answer the last question by Patrick Benz. Can you describe if at present greenhouse gas emission trends, are we expecting to experience the higher ranges of global warming, RCP 6 and RCP 8.5? And so RCP 8.5 is the high emission scenarios that we were talking about, or that we're showing in the tools. And actually on our present track is even above the highest emission scenario that was run in the global climate models. And the low emission scenario is if we have global coordination and mitigation efforts to improve what's going to happen in the future. So currently we're on a track that's even above the high emission scenario that's been run in the global climate models. And I guess that's what I wanted to answer. So that's what we're currently even higher. So.
All right, great. Dr. Allen, are you, do you want to respond to the previous question? All right. So I guess if this is actually communication from Dr. Allen. So in future talks, we'll deal specifically with testing and developing new crop varieties. So Carl and Rosalie, y'all can at some point log on to some of the other webinars which are coming up and maybe have some of your more broad questions answered. So I'm actually going to share my screen again. This time I'm going to share with you the full webinar series, which is on the REACH page. It's at www.reachpna.org, and REACH is REACH/webinar series or /webinar series advances dryland farming with a dash in between. All right, everybody. Thank you for showing up to the webinar, and thank you very much to Drs. Liz Allen and Catherine Hegovich for their illuminating discussion on climate considerations for dryland farmers.
Thank you all for attending and being interested in climate projections for the Pacific Northwest and agriculture.
Yes, thank you everybody for attending. And again, thanks to our presenters and the excellent job they did. And one last thing before I head out, I also want to say that we will probably have continuing education credits for at least some of the future webinars. So if any of you had questions on that, that is the answer. And if you have any questions about the webinar, please email me at bpeterson@sref.info.